Before we proceed to other concepts or the next concept of limits, rather, let's first have a review of what we have talked about so far. So say for example, we have this graph of the function y is equal to f of x. We say that the limit of f of x as x approaches c is equal to a certain number L if, as the x values gets closer and closer to c, the f of x values gets closer and closer to a certain number. So that's the informal way of defining our limit. Now, if our function is quote-unquote well-behaved, unlike what we're seeing now, then all we need to do is do direct substitution. That is, the limit of f of x as x approaches c would be equal to f of c if our functions are well-behaved. That means that whenever we do the substitution, there is no undefined value. However, if the undefined when we do substitution and the undefined value comes out, we usually do some other techniques first before we say that the limit does not exist. First off, we try to see first if we factor and then try to cancel out some common factors. And then we do substitution, then probably it will not be any more undefined. Or if we do rationalization, we rationalize, and the rationalized outcome does not anymore give an undefined answer when we do direct substitution, then that's another technique. We also have special trigonometric limits, special trigon limits, wherein the application of the special trigon limits would help us find the limit of the trigonometric function without easily declaring that it does not exist. There you go. If these three techniques do not work, then maybe what we need to look into would be the one-sided limits. Here, we have here our left hand limit because it's coming from the left side, while we have here you go, our right hand limit because it's coming from the right side. In symbols, that would be the limit of f of x as x approaches c from the left, while the right hand limit is the limit of f of x as x approaches c from the right. And by a certain theorem, the existence of the limit, before we say that the limit do exist, then we have to show that the limit of f of x as x approaches c from the left should be equal to the limit of f of x as x approaches c from the right before we say that the limit of f of x as x approaches c exists. Otherwise, if they are not equal, then the limit of f of x as x approaches c does not exist. Now, let's take a look at the function y is equal to 1 over x. Here we go. This is the function y is equal to 1 over x. Let's examine what happens to the function as x approaches 0. Because as you can see, it's not just one graph, rather it's divided into two curves. And as we can see here, as we approach 0, something is actually happening. So, as our x values gets closer and closer to 0, as you can see here, they get closer and closer to 0. The f of x values actually goes down, because as they get closer and closer to 0, their numbers would actually go down. Maybe I'll use the red color here. For example, this point here, that's very close to 0, but its y value is actually here. Another one, let's pick this point, which is a bit more closer. There you go. And its y value is here. So as the x values gets closer and closer to 0, the y values tends to go down below the vertical number line. And we know that if it goes and goes lower and lower and lower, the mathematical term for that is that the values decreases without bound. Without bound. And these values, as they decrease without bound, they eventually turn or go to negative infinity. So, as we can see, as the x values on the function y is equal to 1 over x, as the x values from the left, mind you, this is from the left, as x approaches 0 from the left, the y values or the f of x values decrease without bound, or they actually approach, let's use another term for this, is that the f of x values tend to approach negative infinity. On the other hand, if we are to take a look at the x values rather, as x approaches 0 from the right, for example, this point here, that's the x value of this point here. Its y value is 3. Here you go here. And if we are to look further, let's say this point, oops, sorry, there you go. It's way above, because it's already, the y value is here. So here, as your x values gets closer and closer to 0 from the right, your f of x values this time increases without bound. Without bound. And as they increase without bound, our values go closer, or they approach, the f of x values approach this time positive infinity. These concepts are the concepts behind infinite limits. Let's first define infinite limits. So, we have these following theorems that if n is any positive integer, then the limit of 1 over x raised to n as x approaches positive infinity is, as x approaches 0 rather, from the right, is equal to positive infinity. Because, let's move that, then let's have a graphical representation. Most of the functions, or most of the graphs rather, of the function 1 over x raised to n will have this curve. Oops. My hand is a little shaky, but we'll have this curve here on quadrant 1, on the positive x and the positive y axis. So, whichever n is, it will always have that curve, and it will always have this end that as x approaches 0 from the right, the y values would approach, the f of x values would approach positive infinity. Therefore, the limit will be at positive infinity. On the other hand, we see here that the limit of 1 over x raised to n as x approaches 0 from the left is positive infinity if n is even and negative infinity if n is odd. Usually, if n is odd, just like 1 over x, because that's x raised to 1, the curve is here at the third quadrant. This is where n is odd. So, as we can see, as our x values go from 0 from the left, we have the f of x values heading or approaching to negative infinity. However, if we have 1 over x raised to n where n is even, the curve would usually look like this. It would be on the second quadrant. And on the second quadrant, as we can see, as the x values tends to go towards 0 from the left, the values would approach positive infinity. The f of x values would approach positive infinity. That's why in this theorem we say that if n is odd, the limit of 1 over x raised to n, 1 over x raised to n, as if n is odd, would be negative infinity. if n is even, at positive infinity. Now, if we look at the other theorems regarding infinite limits, it's saying how we proceed if there will be operations involving them. For example, here, if the limit of f of x as x approaches c equals L being any constant, and the limit of g of x as x approaches c would be equal to either positive or negative infinity, then the limit of the addition, and actually including subtraction, the limit of the sum or difference of the two functions would just be positive infinity. Why is that? Remember, in our limit theorems, this is actually the same as the limit of f of x as x approaches c plus or minus the limit of g of x as x approaches c. With this in mind, this will actually become L, which is the limit of f of x, plus or minus infinity, which is the limit of g of x. And thinking about it, remember that infinity is not a number. It's a concept that says our values either increase or decrease without bound. So if L plus infinity, that simply means you keep on adding and adding and adding and adding and adding and adding to the higher values to N. So you're still going to infinity. You're just adding N. That's why L plus infinity ends up to positive infinity. And similarly, if you subtract from L a lot of values, it will just end up to negative infinity because the values keep on decreasing without bound as you subtract a lot of very large numbers from N. That's why, technically speaking, or not technically, but a shortcut way of thinking about it, L plus or minus infinity would be just equal to positive or negative infinity. When it comes now to multiplication, as you can see here, it's the same basic rule when it comes to multiplication. If L is the constant, and then if g is positive infinity, the limit of g of x is positive infinity, then if L is positive, positive times positive, that's positive, but positive infinity. Because it's the same concept as addition and subtraction, you just keep on multiplying L to very large numbers, positive large numbers, so it's just going also increasing without bound. So positive constant times positive infinity, positive infinity. Negative constant times positive infinity becomes negative infinity because you keep on multiplying a negative number to positive numbers, and that would be negative. On the other hand, if the limit of g of x is negative infinity, and you multiply that to a positive constant, you multiply negatively large numbers to a positive constant, then you're going to get negative, because negative times positive is negative. On the other hand, if L is negative and you multiply it to negatively large numbers, negative times negative becomes positive. That's why this is a positive. This is positive infinity. The same concept for division also happens with these four. If L is positive and g of x, if it's 0, but the positive value, when you do approach g of x at c and it's positive, positive divided by positive, positive. If L is positive, but when g of x, when the limit of g of x is 0, and when you approach c, the values are negative, a positive divided by negative, negative, and so on as well. So let's have some examples of infinite limits here. For number 1, we are asked to evaluate the limit of 3 plus 1 over x squared as x approaches 0 from the right. From limit theorems, we know that this would be equal to, let's write first, sorry, that is the limit of 3 plus 1 over x squared as x approaches 0 from the right. This will be equal to the limit of 3 as x approaches 0 from the right plus the limit of 1 over x squared as x approaches 0 from the right. We know that the limit of any constant is the constant itself, so that's 3, plus this based from our previous theorem, since it's coming from the positive, it approaches 0 from the right, so it will always be positive infinity. So this becomes 3 plus positive infinity, which we know will end up as positive infinity. Therefore, we say that the limit of 3 plus 1 over x squared as x approaches 0 from the right would be equal to positive infinity. If we proceed to number 2, we have the limit of 5 over x squared as x approaches 0 from the left. We can think of this as the limit as x approaches 0 from the left of 5 times 1 over x squared, which we know this can be separated as the limit of 5 as x approaches 0 from the left times the limit of 1 over x squared as x approaches 0 from the left. The limit of any constant is the constant itself, so that's 5 times, in this case, this is approaching the left. So if we take a look at the theorem, if x approaches 0 from the left, if n is even, it's positive infinity. If n is odd, it's negative infinity. Since this is squared, this is even, from the left, this is still positive infinity. And multiplying 5 to usually very large numbers also just tends up to increase without bound. So this is still equal to positive infinity. Therefore, we say that the limit of 5 over x squared as x approaches 0 from the left would be equal to positive infinity. There is a different treatment when it comes to numbers 3 and 4. So for example, in number 3, we are looking for the limit of x plus 1 over x minus 1 squared as x approaches 1 from the left. Since this is a rational expression already, we have to check it. We have to check for the numerator and in the denominator. That's why this, by limit theorems, is going to be equal to the limit of x plus 1 as x approaches 1 from the left over the limit of x minus 1 squared as x approaches 1 from the left. And the numerator, this gives 2, but in the denominator, this gives 0, which makes this undefined. And based on our theorem here, since we have the value of 2 which is positive, it can either end up like this or like this. Now, let's check what happens to x minus 1 squared as x approaches 1 from the left. So we get values from the left of 1. For example, say 3/4. If we get 3/4 minus 1 squared, this will still be greater than 0 because that will be negative 1/4, but negative 1/4 squared is still greater than 0. If we get this, let's say 0.01 minus 1 squared, since that is squared, it will still end up as a positive number. Therefore, x minus 1 squared as x approaches 1 is positive. This function, quote unquote, g of x minus 1 squared, would be positive. So positive divided by positive is positive. Hence, we can conclude based on the theorem a while ago, L is positive, g of x is greater than 0 as x approaches 1 from the left. Therefore, we conclude that the limit of x plus 1 over x minus 1 squared as x approaches 1 from the right is equal to positive infinity. For number 4, which I've already written the given because it was there on above a while ago, we have the limit of x minus 2 all over the square of x minus 1 as x approaches 1 from the right. So again, to first analyze this, we can separate this into 2. The limit of x minus 2 as x approaches 1 from the right divided by the limit of x minus 1 squared as x approaches 1 from the right. above, this becomes -1, while this becomes 0. So we have now to analyze what would be the sign of x minus 1 squared as x approaches 1 from the right. For example, if we have 2, that's 2 minus 1 squared, and that would be positive. If you're going to think about it, any number, once you do inside the operation, then you square it, it will still end up as a positive number. So therefore, we can say that x minus 1 squared would be greater than 0 as x approaches 1 from the right. And since this is a negative constant, but this is positive, by the limit theorem, this becomes negative. So just checking that, it's negative because it's less than here, but then g of x is greater than 0, so this becomes negative infinity. Therefore, we say that the limit of x minus 2 over x minus 1 squared as x approaches 1 from the right would be equal to negative infinity. Now, one application of infinite limits would be the vertical asymptotes of the graph of a function. We define a vertical asymptote as the line x is equal to c if at least one of these statements is true. Previously, in your previous courses, asymptotes has just been defined as the line that the graph tends to touch but never actually touch. Although that's a bit informal and it doesn't happen all the time. What is definitely true is that as your graph of the function approaches the line x equals c, and it tends to go to positive or negative infinity, then that line x equals c is a vertical asymptote. You just need to fulfill one of this to show that the line x equals c is a vertical asymptote. Let's try number 1. We have f of x is equal to 3 over x minus 3. The first thing to do is to check what is c. And usually for vertical asymptotes, if you remember, your vertical asymptotes, I'll abbreviate that as VA. Your vertical asymptotes are actually those that are not part of the domain of your function. So that would mean that if a certain x value is not part of the domain of the function, it might be that in that part of the graph there is a vertical asymptote. Let's verify. Here we have x minus 3, 3 over x minus 3 as our expression for the function. If the vertical asymptote comes from those x values not part of the domain, that would mean that we need to get the values of x that is not part of the domain of this function. Since this is rational, those who would make the denominator not equal to 0, equal to 0 rather, let's use that. Equal to 0 would be not part of the domain, or would not be part of the domain rather. So therefore, we can easily solve that. X minus 3 equals 0, x is equal to 3. So 3 is not part of the domain. With that in mind, let's check if the limit of 3 over x minus 3 as x approaches 3, say from the right, would become positive or negative infinity. You can choose from the left or from the right, any, because we only need at least one. So 1 would be enough. So since we need to check this one out, and this is a rational expression, we do what we did in our previous two examples. We can now separate this as the limit of 3 as x approaches 3 from the right over the limit of x minus 3 as x approaches 3 from the right. We know that the one in the numerator is 3 and the denominator is 0. Now what happens to x minus 3 as x approaches 3 from the right? If we have, say, for example, 4, that's 4 minus 3 is equal to 1. If we have 4.75, that's 4.75 minus 3, and that becomes 1.75. These two will show up positive values, and we know that if we subtract bigger numbers from 3, that's from the right, we get positive values. That's why this becomes greater than 0. So x minus 3 becomes greater than 0 here. And since the numerator is also positive, positive divided by positive, this gives us a positive infinity. Therefore, the limit of 3 over x minus 3 as x approaches 3 from the right is positive infinity. And this is enough to therefore conclude that x equals 3 is a vertical asymptote of the graph of f. Number 2 will be left to you as your own practice to check what will be the vertical asymptote of that function. So that's about infinite limits and vertical asymptotes.